that we were just talking about. So here's what your lab is going to be. So basically what you're going to do is you're going to have a variable power supply for your voltage of your base, and then a variable power supply for your collector. So again, just like what we're talking about, is what you're going to do is you're going to set up your base current so that you have 50 microamps. That's going to be your first step. So what you're going to do is just measure your voltage across your resistor until you calculate out 50 microamps. And once you set that 50 microamps up, that one just stays put. Then you're all done for that one until you run through this cable. So then what you're going to do is you're going to set your base up for 50 microamps of current. You're going to be putting your voltage across you're going to be measuring your voltage across your collector. That's going to be what we call we can also call those our shunt resistor. That's where we're converting it from voltage into current. Then it gets computed. So you're going to be measuring that, and you're going to be measuring your 2 volts across your CDE. So what you're going to do is your first step is you set it up for 50 microamps on your base. You come over here, you put your voltmeter across your CDE. You adjust this. You don't care what the voltage of your source is. You just want to get it so that you get 2 volts across CDE. Once you get that 2 volts across CDE, you measure your voltage across R2, and then just use an Ohm's law, you calculate out what your IC is. And then you're just going to go ahead and do that all the way down. Then you're going to do it for 100 microamps and do that all the way down. Then you're going to do it for 150 microamps and do that all the way down. Now that's your chart. And then when you're all done, then again, just because you guys like Excel so much, we're going to graph that.
Oh, gee, thanks.
Yeah.
Sure.
Yeah. Okay. So it isn't too bad. Here's our. So remember, when we're looking at our diode characteristics curve. If you write this stuff in there, your graphs will go a lot easier if you know what it is that you're looking for. So we know that we want voltage of CDE. We know that we're going to have three lines. These are our data series right here. We're going to have 50 microamps, so that's going to be your series 1. You're going to have 100 microamps, that's your series, that's another series. And then your 150 microamps. Okay, so these are all our series. These are what gets indexed to, so we just keep on adding series. Once you add that series in there, then what we're looking for is your collector current, which is going to be equal to Y, and then your voltage of your collector to emitter, and that's going to be your X values. And this is going to be our data series. Okay? So this is going to be, here's your X, here's your Y, and then these are going to be your data series. So if you write that stuff on your graph, then it isn't so hard to graph it out. Then you already know what you need to do when you're creating your graph. So when you're all done with that, then your graph should look something very similar to this.
One more time?
No. I can't go home.
So that's what you should end up with. That's going to be your characteristics curve for your transistor. And then, since you already know, that probably I'm going to hide that. Ignore the beta DC, don't ignore that, that's something different. But we know that we're set up for our base at 50 microamps. So we can go ahead and figure out, you can go ahead and you can calculate all this all out. You can figure out what your beta is then, the actual beta of your transistor. So we know that we have 50 microamps, and we can take any one of our collector currents. You can see that the numbers for our collector of our current, even as I increase my voltage across CDE, that current is still staying pretty close to very similar. Remember, there's that slight angle that's going up. As I start increasing my voltage across my collector to emitter, my current starts to go up on my collector current starts to go up a little bit. So I get a slight angle up there. So that's my gain. That's going to be how much my gain is at. But it stays pretty flat. My gain is going to be pretty flat. So you could go ahead and, you can try and, put in that whole beta in the same one. So let's just do one here. Let's zoom in here. So once we get the data, then we can, manipulate more of our data. So I'm going to just insert a column to the left. And I'm going to call it my beta DC. And then to calculate out what my beta DC for my particular transistor, because like I said, everyone's is going to be a little bit different. I'm going to hit equals. And how do I calculate out beta DC? What's my formula for beta DC? What's the ratio for beta DC?
IC over IB.
Yeah. Yep, so IC over IB. So all I have to do is just take my IC, which is going to be right here, this number there, and divide it by my, I'm going to have to cheat here, because this is a text file, so I'm going to just put in 50 e to the negative 6.
You gotta erase the cell number.
Yeah, because I don't want to read that 50 microamps. It's going to read that as text. So I'm going to just put a hidden one in here. 6. I'm going to just go equals this divided by this. Accept it. And there's going to be my beta for my particular transistor. If I click and bring it all the way down, gotta change it, make sure that's E2. Sweet, down. Get my dollar signs in there. Okay. So you can see that as I start increasing my voltage across my collector to the emitter, it's changing a little bit, but only by about, 17 and stuff. So it stays pretty consistent and stuff. And so now you can go ahead, and now here's the actual numbers. And so when you get into Lab 34, then you can use these numbers for calculating out your actual beta DC. So when you're doing your approximations in your Lab 34, you actually do have the beta DC for your particular transistor. And then you can use that for approximation. So a lot of times we do end up using the actual values for beta DC. We actually put them on the curve tracer and then take a look and see what our actual beta DC is, since that's our gain. Yeah, certainly, yeah. Well, you don't have to put your gain, no, you don't have to put the gain on the graph, but you should have a column in there so you can see what it is. Alright? Alright, so that's the manual method there. That's the hard way to do it. And there's your graph, and everything else is about the same. Here's your calculating out the current gain for at 3 and 5 volts, but we can do the whole thing right off the bat. So that's all that lab is. So it should go pretty quick. We should be getting pretty good with Excel. All we have to do is hook up the circuit, measure it, put the data in there, and then graph it up. All right, so let's take a. So now if we do it in the real world, now everyone should have gotten the copies for. I put them out on the Google Drive there. You should have grabbed all the curve tracers. Here's the Ni2 wire one. That's the one that we just used on the diode curve tracer. Okay. The other ones that you should have grabbed at the same time were the BJT one and the fat ones. The one that we're looking right now is just the BJT one, the curve tracer. So I'm going to open that up, and that's going to be an actual. This is some professor out. I think he was out east there. That I got this one from. But this is just again. This is one that he puts out there for open source for us anyone to use. I can't sell it or anything like that, but I can. But we can use it in our classroom and stuff. And so this is a curve tracer that he designed. Now again, just like when we're working with all our IDEA custom VIs, you're going to have to set up your data acquisition, and you should be getting pretty good now about getting around in your LabVIEW now. So, I know that's pretty. I know that's pretty basic, doesn't it? I know compared to what you guys are doing. Yeah. All right. So you still should be able to.
Just copy that. Here's my homework.
Yep. There you go.
Look at what I built over the weekend.
So we know that we have to. What we're going to do is we're going to have to set up our data acquisition so that we can, because what he used was the NI Elvis. We're going to use the MyDAC. So we have to reallocate our analog outputs and our inputs. I'm going to go back and I'm going to show you his he's got some documentation here. So if I open up that, so in that folder I also gave you his documentation. Here's his PDF. And it talks about the whole theory of operation of the curve tracer. I'm just going to scroll down. And then here's how he's showing you how to hook it up. That hookup is the same as what we just did in Lab 33. It just looks a little bit different. So what we're looking at is that here's our circuit. I'm going to redraw that circuit on the next side. So even though that, so when we get these, when we download somebody else's source code or something like that, sometimes we have to make changes to it so that we can use it for our own purpose. They designed it for their application, and we can go ahead and just modify it so it works for our application. But you have to understand the mechanics of it. Again, sometimes we have to redraw things out so that we can see what's going on. Here's VCC, BBB, RB, RC. All right. So the test setup then is here's our analog ground. So already we know that this is going to be my analog ground right here. So we know that both VCC and BBB are going to be both tied to analog ground. Here's my analog outputs. Here's channel 0. Here's channel 1. And we're going to come off, make sure you remember, we always come off of our op amp, not off the analog output right from our MyDAC. You have to go through the op amp, otherwise you're never going to get enough current going in. So my analog, so we'll just do the log lower. So my analog output, channel 0, is powering up my VCC. So here's my A ground, and then here's my analog 0, channel 0. Okay, that's going to power up my. That's going to power up my collector. Then channel 1 is going to power up my VVB. So that one's going to go here. So that's going to be analog 0, channel 1. Then we have to do some. Then we also have to do some measurements. We have to get so we can calculate our collector to emitter and our current going through our base. So he doesn't really. So what he's doing, because we don't have enough inputs and outputs and stuff like that, what he's doing, he's kind of cheating a little bit. He's just kind of taking the voltage of the. See, so this one here is his voltage. So he's taking his voltage of his base, and he's hooking that one up to our analog input pin 7. So he's going into here, and he's monitoring analog. So this is going to be, because we only have a couple analogs, so this one's going to be our analog input. I want to make sure I do this right, so matching up with mine. Got pin 7, so this one's going to be our analog input, and we have +0. He doesn't have the -0. This is just referencing his A ground. So our analog for this one here, we have to make sure when we're doing analog input measurements, it's the differential of the two inputs. So we got the +0 and the -0. So we know that that also then has to be tied to our A ground. So our analog out is going to be, or our analog in is going to be on our -0. We're going to tie that one to our A drop. Then he's measuring the voltage of the collector, and he's coming across here. And this one's going to be our analog input +1, and then the other one has to be tied down to our ground, our analog -1. Okay? So in his code, he's already going to know, in his code, he's already going to know what his voltage of his DCC is, and so he can just go ahead and take whatever his voltage of his collector is, minus his, or take his voltage of his source, of his collector source, subtract the voltage of his collector, subtract that, and then he's going to know what that voltage across RC is. Once he knows what that voltage of RC is, then he can take that and divide it by his 1 kiloohms, and then he can calculate out what the current of the collector is. Same thing here. He's going to know what the voltage of the base is. He knows what his voltage of his base source is. He's just going to take his VVB, subtract his VB, and that'll give his voltage across his RB, and that'll give him his current. So then we have our IB calculated out, our IC calculated out. We have our voltage of our collector to emitter. That's going to be from here to here. The difference between this and what he already knows, what he set that up, that's going to be his voltage of his collector, VRC. And the same thing here, this is going to be his voltage of RB. It's just going to take the difference between whatever he set his source voltage up at, and then subtract his base voltage. So a lot of times when we go through it, this is when I first downloaded this program, this is exactly what I did. I drew it all out. I figured out what I had to do. I knew that my AI 0, this one I knew was going to have to be my AI +0. I knew that this one here was going to change to my AI +1. I knew that then I had to reference my ground on both of them. And once I got up that test circuit then and figured out what I did, then I went into his program and I changed those the appropriate value so it would work out for mine. Like I said, he was using the NIL bus. You can see that he had pin number 57 and pin number 25. Well, that means nothing to us. But everything else does. His analog inputs and his analog outputs. So once you determine that, so then that's basically that same circuit is exactly what he's doing here. So now we're going to go back into the program. So here's this code. So you think anything? Can you see anything obvious that would make sure kind of lead us to where the dash might be? You don't see any sub DIs. You guys did do sub DIs so far, haven't you?
Yeah.
See any sub DIs that might over here?
Mm-hmm.
How about measure one? BJT measure one.
Let's try that.
Let's try that one. Yeah.
Wrong.
So double click on that. Go to Windows, show block diagram. Hey, there's our data acquisition. Okay, that's what's doing our measurements. That's what's putting out our. This is what's going to be putting out our VCC, our VBB, and doing also our measurements of VB and VC. So, what kind of structure do I have here?
Case structure.
Case structure. All right, good. So what I'm going to do is I'm just going to go to my first case, my first case, which is 0, and I'm just going to double click on that. And I have to change my VCC so it matches up to what our MyDAC is. So I'm going to just open that up. And he's already got it all named out and stuff. I can go ahead and delete that and add it back in. And that's what I would have to do when you first start out. But there's actually also another way. We can go ahead and just click on the edit button, and we can edit it. Now, obviously, I already set mine up because I tried, played around with mine already. But I would go ahead and you can have to select. I want my VCC to be my analog 0, channel 0. That's going to be my analog output. And then I'm just going to click OK, and it's going to build, and we'll be done. Okay, then I'm going to do it again. Then I'm going to go to my VBB. Double click on it. Click on edit. Then tell us to go to analog output channel 1. And build it. A lot of times what you'll end up on this one here is, for some reason it doesn't recognize the data type. A lot of times you'll get the broken line. You're going to have to rewire that back up. And you just bring it over from your node there and then bring it down to your data there. Okay, so now we've got our 2 outputs reassigned, and then we have to reassign our inputs. You just click on there and then go to your analog channel 0, like that. Say OK, let it build. And then do the same thing with your VB. Okay, then once you get all that, you can go ahead and close that, close this, take save, close this one here. Alright, so here's, I did save you a little bit of work. If you look in his documentation, he's going to have his set up for a little bit slightly different. So I set mine up so that it goes pretty close to what ours is. So what I did is because I wish it would save the value. I'm going to go and put in some of those values and save them. But if I go, what I did is, so I can duplicate my thing again. If I ever need to duplicate it, or again, every year when I come through the year, I'm not trying to relook it up to figure it all out. I made a screenshot of it. This way, if I set this up, then I know that my VB steps are going to automatically calculate out to my 50 microamps, 100 microamps, and 150 microamps. Because he's not giving us, because he's doing it a little bit differently than what we do, is that I had to go ahead and recreate that. So in our lab, what is that? 33K, I think RB is a 33K. Anyone have their lab book open for that on the curve tracer one?
Yeah,
33K. So I know that my first step here, I want to have it as 50 microamps. So I know that I had to have 50 microamps here. So I'm going to have 50 microamps here, and what would be my voltage then across RB that I'd want to see? So if I got 50 microamps times my 33 kiloohms, what does that give me for voltage?
.65 volts.
Yeah, 1.65 volts. Okay. Well, we're looking at my voltage of my base source, my voltage of my source for my base, and we're looking at the VBB. So I have to set up my VBB to be, and you can see on there I have it as 2.35 volts. So I would have to set up my source voltage on my base there for 2.35 volts.
Is your diode?
Yeah, because of my base to emitter junction. I have to include that 0.7 volts in there. Because when I apply 2.35 volts, 1.65 is going to drop across RB, and then 0.7 across my base to emitter. So then I knew that my VBB start then was going to be at 2.35 volts. Then I did the same thing for my VBB stop. Then I did the same thing. This time I went to 150 microamps. Now what's my voltage going to be at 150 microamps across RB?
.95 volts.
4.95 volts. And then I have to add 0.7 to it, and that gives me a this is 50 microamps. And this would be 150 microamps. And this will give me my 5.65 volt. So that's going to be my stop there. And that's going to give me 150 microamps. This will give me my 50 microamps. And then I want it to look like my graph that I just created in my Lab 33. I only want 3 steps. And so then I just told it to put 3 steps in there. And so now I'm going to get something at 50, something in between there, and then 150 microamps. And then I also had to tell it to put in my 33 kiloohms for my shunt resistor, so I knew how to calculate everything out, especially my current at my base and stuff like that. And then this one, I wasn't so worried about these numbers here, because those are just going to be taking some samples. But it's going to start out at 0, and it's just going to start increasing my source voltage, and it's going to measure what my collector to emitter voltage is, or my DC, because DC, on this particular circuit, DC is equal to VCE. So really, it'd be nice if you had this as labeled as VCE, so people really knew that's exactly what we're looking at. We could go ahead and change that. Okay, so all I wanted to do is I just wanted to run that from 0 to 10 volts. That was our maximum amount of voltage that we can put out of our MyDAC. And then what I did is I set up, well, then I put in my resistor of 100 ohms, so it matches up my lab. So I got 100 ohms in there. And then what I did is I just kept on adjusting my VCC points until I got a VCC step of 0.25. So what it's going to do now is it's going to, when it starts running through, it's going to go 0.25, 0.5, 0.75, 1, 1.25. It gives me some nice logical steps, but if I change that, then my VCC steps are going to change. But I like kind of nice round numbers, so I just kind of threw in some numbers until I got that to equal up to my 0.25. Then I give it a delay of about 5 milliseconds to give it a little bit of time. So once I got that all set up, I remember all this now. Once I calculate it all out, put in my values here, so I got 5.65. I've done it a lot. Yeah. All right, so now if I go ahead and run it, if I got it all wired up right, so I got to make sure I wired it up the right way. Nothing fell off. Since I wired it up, it should be in good shape. And there you go. And there's the only difference is that remember we don't see these lines. Because we start out at 2 volts on our graph on our lab, so we're going from here over all the way up to the 10 volts or 8 volts, whatever it is. But there's that same graph, and I should be very close to what I'd get on my other lab. Now, obviously, I've changed my transistor around since I've done my Excel spreadsheet and stuff like that, so my gains aren't quite the same. But if I go ahead, and what I can do then is I can go ahead and I can save the data. So once I get done measuring it and I see the graph and it looks good, then I can go ahead and click on Save Data. I'll just put this on my desktop. Give it a name. And you got to name it so that Excel can see it. So we'll just call Lab 33. Bullshit. This is good information. Then give it an extension of .csv, common separated value. This is good stuff. This is what you're going to do out in the industry. So now if I open it up, then there's all my data. Now in his book there, he's got documentation about what all these columns are. But here's my VDD, because I can tell you that's my VDD, because there's my 2.35 volts. So my first column is going to be VDD, VCC, VV, VC, and then IV and IC. But once I take all that data, I could go ahead and I could re-graph it out if I really wanted to. Or I could just use it for the information I need. So I happen to have already done that too, so you don't have to see me doing all that. So there it is. I just went ahead and I took my data that I collected, I retitled it, I put some titles up on row 1 so I knew what I was looking at.
So that's a curve tracer?
That's all from the curve tracer. This is all the data from the curve tracer. So now I can use it for anything. So now, if I'm designing something, and I want something with, if I know that my collector current is going to have, 6 milliamps of current going through it, I know that my beta, now I can go ahead and calculate out my beta, and you can kind of see that my beta, all the way across my whole curve tracer, is anywhere from about 134 to 137. But I can go ahead and I can calculate out all my beta. And I can calculate out my alpha DC, but we'll talk about alpha DC on Wednesday. But go ahead, this is what we use our data for. So now I can go ahead and I have all my data. I know exactly what the data DC is going to be for my particular transistor. Like I said, now Tyler could go, he could throw his in there, and you might get 187. Yep. Josh could throw his in there, he might get 150. So it all depends on from transistor to transistor. But we use that data, and then we can use it for analyzing a little bit more, not just to look at pretty pictures, but to actually get some real numbers and stuff like that, and use those numbers for our approximations. Or as Brad says, it my bullshit.
Someday you'll regret it. Someday you'll go, hey, yeah, you remember that time when you... Yeah.
All right, I'll let you go. I've bored you guys enough. Brad started up these